All right. So we have just two topics left to cover. So I pulled a switcheroo in the schedule. um, okay. All right. Just switching sections 8.5 and 8.6. I'm going to cover 8.6 today. 8.5 Gauss Quadrature is a difficult topic to digest, and I'd rather have cover that when there are more people here. And also, I just talked about composite rules last week, and 8.6 builds directly off of that, so it just kind of made sense. Okay, now, there's still a number of people who have not yet turned in homework 3. I've just received a couple more submissions today, but like a majority have. But so the ones that have been submitted, I will do my best to have those. I should be able to get those graded during the break. So, but there is a homework 4. Let's not forget. And there's still some time before it's due, but you want to get on it soon. And then I know there's still some Canvas quizzes submitted. I'll get those graded shortly too. All right. Okay. Does anyone have any questions about anything at this point? Whether it's the upcoming final or any homeworks, let's just get any questions out there.
Could you explain a little bit more about how the oral final works?
I kind of figured somebody would ask about that. I've gotten a little bit of interest. Okay, so the way it works is, so we'll just set up a time. We'll block off an hour, but I probably wouldn't take all of it. But still a fair amount of time. Like it could be up to probably 45 minutes or so. Where and what I will do is I'm going to go through the different areas of a course. Not really Matlab, but error analysis, computer arithmetic, polynomial interpolation, differentiation integration, and ask you a selection of questions about each. Where and I'll go ahead and write this down also. Okay. Okay, and so for those of you who choose that, I think only one person is definitively committed to doing it. But it could be up to a last minute thing. Okay, I'm going to have a condition about that. You need to make up your mind about this by the time of the written final. The one during finals week. So must decide which by Tuesday, December 5th. I don't want a situation where someone goes ahead and spends the 2.5 hours taking the written final, and then they bomb it. It's like, okay, the whole second bite at the apple thing. So each one of you gets one bite at the apple. Whether it's an oral bite or a written bite is your choice. But that's in the interest of fairness, this is how it works. Especially since. Sorry, what?
What is the oral final?
Oh, okay. I don't know if you've watched the video from the last class yet, which is where I brought it up for the first time. Okay. Well, I'm gonna be reviewing what I said now. Anyway, so okay. So the idea is, and I don't know if you've also seen the video where I talked about how the written final is going to work. So to recap that real quick. Okay, so I'll just fill in both these here. Written final will All right. So it will begin on at last, let's say 40 minutes of class on Thursday, November 30th. So our last regular class meeting, first part of the class will be review. And then I will actually hand out the finals so that you can get them started. I will be at the coast on that day, and we have a substitute up here in Hattiesburg who will give them out there. And the idea is you will get to start the final during that time, and then at the end of class, I will gather them up, and partially grade them. So finals with my feedback. So like I'm not going to put a score on it or anything, but I can say like here you're going about this problem the wrong way, or you're doing it right. Will be completed at the regular university final schedule time, Tuesday, December 5th, 4:15 to 6:45 p.m. So so on the coast, I will give Ms. Nakeen the marked up finals, and she will redistribute them to you with my feedback on them for you to complete. And then she'll I'll ask her to scan those to me so I can get all of them graded quickly. Okay, and then the for also still in the written final, 2 sections, regular problems. There's a practice problem on the lectures page. So you can see what to expect there. And then lightning round, those are more conceptual questions. Short answer. And I emphasize short answer because I don't want some big long paragraph. And you don't have time for that anyway. Bless you. Short answer questions. Best, they're like the concept check questions that you've been doing. So I would look at that to get an idea of what to study. Okay. All right, so that's the written final. So each one of you individually gets to choose which one you're going to take, the written or the oral. So for the oral, so 45 minutes to an hour of now both written and oral are comprehensive. So now I can talk more about that since that's the original question that was asked. So mainly, again, conceptual questions. And what I mean by that, certain definitions, also comparison of methods. These are the kind of questions that you see in a concept check anyway. Like for instance, in this current chapter 8, we're seeing various approaches to integration. What are the advantages of one over another? What are the properties of methods? Things like that are what I'm most interested in asking about. Okay. And again, like the concept check questions would be a good thing to look at. But if it's also going to be a little bit of seeing how you think in your feet. Like if I give you something to work out, something where I like for instance working on the board, I would help guide you through it, but in terms of like applying the various things that we've seen, like one thing I could see doing is if I were to give you some x's and y's, like for a polynomial interpolation problem, then I could ask you some questions about the whole process of constructing the interpolating polynomial, like completing a divided difference table, Newton form versus power form, things like that. There wouldn't be much time to really have you actually work things out on the board. That's really more appropriate for a written test. But there will be some questions about applying techniques. I think the main difference between an oral and a written is that in a written test, because there's more time, you'd be focusing on the details and grinding a problem out from start to finish. Whereas in an oral setting, I may have you work out part of a process and then ask you questions about what you're doing. So that's to give you an idea of a contrast between the two. So, so you have some time. Okay, now if anyone at the Coast or Stennis chooses this option, we'll figure out how to implement it. So I emphasize my schedule during finals week, aside from the Tuesday afternoon where this final's given up here. So I am able to head down to the coast if that's if that's necessary. Now, if there's a situation where, because we have 3 students down in Gull Park, for instance, if more than one of you wants to do the oral, ideal situation would be where I can go down there and take one trip and handle all of them in one shot. So it'd be good to have some coordination there. But so if you're still not sure about which one you want to choose, of course you have time to think about it. Over a break and a little bit past that point. Also, can take it week before finals if you would rather do that. And reduce some of your finals week burden. That's an option too. But yeah, feel free to ask me questions about it either here or outside of class if you're trying to decide. Okay. Any other questions about this?
Have you determined how much, what percent of the final will be, what percent of the written final will be
Oh, the lightning round versus a regular. Okay. I'm leaning towards an even split. Or for instance, if there's 8 problems, 8 regular problems right now. If I make them worth say 6 points each, so it's like a 48-52 split. Yeah, something like that. Yeah, there's not going to be a dominant portion here in terms of grade. All right. Other questions? Okay. All right, and actually, just to get an idea, because of course, for those who take oral, the main thing is scheduling. So I guess that'd be the main difficulty with it. So if you feel comfortable in your decision, written or oral, go ahead and let me know, because that's going to give me an idea as to what I'm looking at in terms of how many written finals will I have to give, how many orals to schedule, things like that. I'm not going to pressure anybody to make a decision because there's time. But if you really are sure already, then go ahead and feel free to let me know. Any other questions? All right. Actually, I'm gonna grab some water. Okay. All right. Now, dang it. So what we just saw last time was that after seeing interpolatory quadrature, where we saw like a few examples of these rules, like midpoint, I should say the basic midpoint trapezoidal Simpson's rules. So not effective at a high degree, and it should emphasize especially Newton-Cotes rules that choose all the x values to plug into your integrand to be equally spaced. So we saw composite rules that apply the interpolatory rules on subintervals. With order of accuracy, so now the error is related to, it's going to be proportional to a power of h, where okay, interpolatory subintervals with width h so the idea is, as your spacing h, the number goes to 0, so that your number of subintervals increases towards infinity, then your approximate integral converges to your exact integral. And just to recap, p equals 2 for composite, midpoint, and trapezoidal rules, and it's fourth order for composite Simpsons. Okay. All right. So now we have composite integration rules where that at least are guaranteed to converge to the exact value of the integral as your spacing goes to 0. So what we're going to do is build on that today. So combining one of these rules, the composite trapezoidal rule, with a technique I'm going to show you called the Richardson Extrapolation. So the union of these two techniques gives us, I just want to emphasize anything new that you're seeing today, with called Romberg Integration, which yields higher order accurate results. So the nice thing about Richardson Extrapolation is the main work is done in using a composite trapezoidal rule. It turns out that if you are willing to expend the effort to apply the composite trapezoidal rule more than once, like for different values of h, it turns out to be very easy to combine those approximations to essentially cancel out part of your error, and the result is a higher order accurate approximation. So you get more bang for your buck in terms of the computational effort involved to use a composite trapezoidal rule. And then next Tuesday, the last topic, Gauss Quadrature. That's really that's the techniques that we're seeing. I should say most of the time. There's no clear winner when it comes to numerical integration techniques for all possible integrands, but this one is most heavily favored. Like in professional software, it's most often used. Okay. And then that will be the end of a semester. Okay. So for Romberg integration, refresh your memory on the composite trapezoidal rule. So what you're doing is dang it, went on to another page. Okay. All right, so your exact integral, what we do is, instead of using rectangles to approximate the area under a curve, we use trapezoids. So we're connecting the dots in the graph of f. And that way there's ostensibly less error in approximating an area under a curve with trapezoids than rectangles. So what we have is f of a, and then we take twice the sum of function values at interior points. All right, so this right here is your approximation of the integral. So notice all function values, bless you, are given a weight of h because you have these twos canceling out. So all of these function values are multiplied by h, but the endpoints are multiplied by h over 2. So they're given half the weight of everything else. But this comes directly from a formula for the area of a trapezoid. So the width times the average height. And some definitions, some notation here. H is equal to the width of your interval of integration divided by n. So we have n intervals of width h. And then xi, so these x values that we're substituting in are a plus ih, for I going from 1 to n minus 1, since those are the ones we're using down here. So in fact, what I could do, I could write it this way. It'd be a little more clear. This is a plus ih. Okay. So we're evaluating f at these equally spaced points and then giving them the appropriate weights. And that gives us the area of all these trapezoids. N trapezoids altogether. And that approximates the area under the curve. Now, if there's going to be error, I gave an error formula last time, but here I'm going to represent the error a little differently. So we have some constant, which I'll call k1 times h squared, and then another constant, h to the fourth. And so on. Now, this is something I've not actually taken the time to show here. I did show that the error is proportional to h squared. So I gave a formula for this last time. But so before I go any further, a couple comments I want to make. So this representation of the error that we see is some. Note the key point I want to make: even powers of h comes from what is called the Euler-Maclaurin expansion. You know the name Maclaurin from Taylor series, where the center is 0. It's that Maclaurin. So this is from the actually it's not early, the middle part of section 8.6. I'm not taking the time to cover it here. It's really something I go into more in a graduate course. But what's done here is a monstrous exercise in integration by parts to prove that the error has this form, it's sum of only even powers of h. And then the other thing I want to point out is if a function f is periodic, and the period is Okay. If a period divides b minus a evenly, so for instance, suppose AB is the interval, let's say 0 to 2 pi. So if a function is 2 pi periodic, or a period that is a integer multiple of 2 pi, like 4 pi, 6 pi, etc. So if both of these are true, then the composite trapezoidal rule is the very best integration technique. Beats everything else I could show you. And what I mean by that is the error goes to 0 exponentially. And by that I mean faster than any power of h. Because we like to have higher powers of h in our error. So we like Simpson's rule usually better than like composite trapezoidal or midpoint rule, because the error is proportional to h to the 4th rather than h squared. H is assumed to be small and going to 0, so the higher power, the smaller it's going to be. So when the integrand is periodic, then the error is proportional to h to any power. So, and because that power can be as large as you want, then it goes to 0 especially fast. So exponentially is ideal. Doesn't happen very often. So, because this is really one of the least sophisticated methods for numerical integration, but it turns out for this category of integrands, it's just a whole lot better. Okay. Not sure why our only co-student left, but okay. Now, what I'm going to do now is make use of this representation of the error right here. And for what's to introduce Richardson Extrapolation. Okay, so Richardson Extrapolation is actually used in a variety of contexts. Here I'm going to use it for composite trapezoidal rule, but it can be used for any time you have an approximation that's dependent on a spacing h. So other composite rules or differentiation rules, they depend on a spacing h also. In fact, I'll have an example about that. And this is covered more extensively in the early part of section 8.6. But here I'm just going to use it just for integration. So the general principle is the following. If I have an approximation, I'll call it T of h. So I could, all right, so I'll define it up here. Stop that. Oh, God. This is so aggravating. Okay, T of h be the composite trapezoidal rule approximation with spacing h. Okay. So I could say that, well, and I'll add to this T of 0 is equal to the exact value, because as the spacing h goes to 0, you would get the your approximations would converge to the exact answer. So I'll just use that to refer to the exact. So I'll say T of 0, so the exact integral is T of h plus, and then I have this error representation up here. So I'll just fill in the first part of it, k1 h squared plus, and the rest of it I'm going to kind of neglect. I'll just say it's order h to the 4th, so we'll go with that. Now, what I could also do is, instead of using spacing h, I can use a spacing h over 2. So in that case, I'm going to have constant, k1, and then h over 2 squared. And then what's left is still going to be proportional to h to the fourth. Okay. All right. So the idea is, suppose I've gone ahead and computed these two approximations. Composite trapezoidal rule spacing h, and then I've gone and done it again with spacing h over 2. Okay. Now, I can use these approximations to solve for the exact value by basically canceling out this leading error term here. Okay. So the way I'm going to do that is I'm going to, well, first I'm going to rewrite this. All right, so I'm going to make this fraction. Okay. So what I want to do is I'm going to also neglect the higher order error terms. Okay. All right. All right. So now we have this. So the idea is these two pieces, t of h over 2, these are known. We do not assume that k1 is known, because really it is unknown. Because the error formula, it's some derivative evaluated at an unknown point. But we do know it has this kind of form, that if I cut the spacing in half, then the error is cut by a factor of roughly 4, because this is because composite trapezoidal rule is known to be a second order accurate method. And then this t of 0, of course, that's what I want. So what I'm going to do is I'm going to linearly combine these equations to cancel out these error terms. So what should I do algebraically? Like if I want to scale the second equation, so this second equation here, what should I scale this by so that the error terms can cancel? Times. And then if I want to add the equations together, minus 4, yeah. Okay, so I'm going to scale by minus 4. Okay, so I have minus 4 times that. Whoops. And then I'll have minus, and now this will just become h squared. Okay, so now I can go ahead and whoops, I need to go to another line here. All right, so we're adding these together, and so what we get is, on the left side, we'll get minus 3 t of 0 equals, and then I have t of h minus 4 t of h over 2. So now I can just go ahead and rearrange that. So what is t of 0 in the end? Based on what I have up here. I'm sorry. Okay. Whoops. Okay. So minus th over 3 minus plus. Okay. All right. And actually, I'm going to clean this up a bit. Let's put this term last. Okay. And then I'll make this a single fraction. All right. Whoops. All right. So by taking 4 times a more accurate approximation, because a smaller spacing is more accurate, minus a less accurate approximation, all dividing it by 3 is a 4th order accurate approximation. So this is the idea behind Richardson extrapolation, that if you know the order of accuracy of your approximation, you have some constant times some power of h, then you just use 2 approximations, and here I went with h and h over 2, but you could do h and h over whatever. All that does is affect what you scale by, like how you linearly combine these approximations, and you solve for the exact one. So once once you've computed these approximations of h and h over 2, then there's very little work. You're only doing 1, 2, 3 floating point operations after that. So for very little work, all of a sudden you have a whole lot more accuracy. You've gone from 2nd order to 4. Okay. So the idea behind, so first, any questions about what was done here to get rid of that error? Okay. What? Oh, anyone have any questions about what was done here to get rid of this error? All right. So this idea of Richardson extrapolation is used repeatedly to give you Romberg integration. So the idea is you compute several trapezoidal rule approximations, and then repeated Richardson extrapolations to increase order of accuracy. All right. So what I'm going to do I'm going to now I have a couple of things in the book to call your attention to. So in fact, here is where I carried out, like, showing how the initial extrapolation. Here it's the same formula I just showed you. It's just written in a slightly different form. But if you put all this over a common denominator, you get exactly the same thing. The 4 times more accurate approximation minus less accurate divided by 3. Okay. So what's done is we actually form what is called a Romberg table. It's kind of like a divided difference table in a way. It has a triangular form to it. You're filling out like the lower triangle of a matrix. So what you do is, in your Romberg table, you fill out the first column with a bunch of trapezoidal rule approximations. So here's a Romberg algorithm that computes. It applies a composite trapezoidal rule, and the indices here, capital T refers to approximations, and 2 indices indicate row and column that the approximations go in. So first column, we fill it out with composite trapezoidal rule, and then later columns are filled out using Richardson extrapolation. And one key point I want to make here, I'm going to show you in Matlab how this process unfolds and how effective it can be. But one thing that's key to point out is, when you're using composite trapezoidal rule, and then you decide to cut h in half, well, you're using equally spaced points. So what that means is you're actually reusing a lot of function evaluations from before. And you don't want to waste that. The whole idea is to minimize the number of function evaluations. So I have here proven if I want to use a trapezoidal rule of spacing h, and I've already done it with spacing 2h, all I have to do is take half of my previous value, and then I add the function values from the new points. So that way, there are no function evaluations that are duplicated. So that reduces the amount of overall effort needed to compute the to use a composite trapezoidal rule many times. So I have here in the book an example. Here I have this integral, one of my favorite examples, and how we use composite trapezoidal rule. First with a very simplest approximation. This is actually the basic trapezoidal rule here. And then what I do is, and then I do it again with twice as many subintervals, and then later on twice as many again, and then you can see all the extrapolations being performed. So that's something that you'll want to look at later as far as how to carry out the algorithm. But what I'm going to do here is go into Matlab and show you how it's done there. So you can see the whole process. Okay. So the integral of e to the x on 0, 1, again, one of my favorite examples. So just as a reminder, the just for convenience, I'm going to give myself a variable for e. So then I could just instead of typing out exp every time, I could just go ahead and do e to whatever power I want. So then the exact value is the integral of e to the x on 0, 1 is going to be e to the first minus e to the 0. So it's just e minus 1. Okay, so that's what I'm going for. I'm going to use this to measure error. So the so first column. Okay, I'm going to perform. So the size of my Romberg table, however many columns, indicates how many extrapolations I perform. So for instance, if I only perform one extrapolation, that's just a 2 by 2 matrix. I use a trapezoidal rule twice, and then I extrapolate once. If it's a 3 by 3, I use a trapezoidal rule 3 times. And I perform 2 extrapolations to get me to 4th order, and then one other to get the 6th order. So a j by j Romberg table allows enough extrapolations to get order of accuracy 2j. All right. So what I'm going to do is I want to get up to, let's see, I'm doing pretty well on time here. I'm going to go up to 8th order. So I get a 4 by 4 Romberg table. So I'm going to make a 4 by 4 matrix. Okay. So you need a little more room here. All right. So first column of this table, I'm going to use a composite trapezoidal rule with n equals 1, 2, 4, then 8 subintervals. Okay. So the first time around, so my 1, 1 entry, actually I'm going to do, okay. I use a, okay, so first it's going to be half the width of my, I only have one subinterval, so that's the interval AB. So I take half of that width, which is 1/2, because I'm on 0 to 1, times e to the 0 plus e to the first. So this is the basic trapezoidal rule. Okay, so there's my approximation. And keep in mind, up here is the exact, so not so good. But we should see, as we extrapolate, converging to this value. All right, now, the second one is I'm going to use 2 subintervals. So now I'm going to cut my fraction here out front in half, because it's always the width of your subinterval divided by 2. So then I'll have e to the 0 plus 2 e to the 1/2 plus e to the first. Okay, it's getting better. Because I expect like 1.718, etc. And then again. Okay. So now I'll have e to the 0 plus 2 times. So my subintervals are width 1/4. So e to the 1/4 plus e to the 1/2 plus e to the 3/4. Okay, so getting better still. Now, to show you how this is done more efficiently, because if I just keep going to do the next one, right now I have 1, 2, 3, 4, 5 evaluations. The next time around, we're going to need 9. But look at what happened here. Look at the waste. Here I evaluated x equals 0, 1/2, and 1. Here again, 0, 1/2, and 1, and then a couple of new points. I don't want to do that again. I want to reuse these values and only add the values of e to the x at the new points. So I'm going to go back to my formula here. This one, where I can take half of my previous value and then my, my new spacing, which will be, all right. Oh, okay. Yeah. My new spacing, which in this case will be 1/8, and then times the sum of my function values at my new points. So those will be like 1/8, 3/8, 5/8, 7/8. So I'll take 1/2 times my previous value, which I just computed up here, and then I'll have my h, which is 1/8, because I have 8 subintervals now, and I'll take e to the 1/8 plus e to the 3/8 plus e to the 5/8 plus e to the 7/8. And if I did this right, I should get something that's closer still to e minus 1. Yeah, because the exact result is 1.718, so we're definitely getting closer. But before I go any further, well, first, any questions about carrying out the trapezoidal rule so far? We haven't done any extrapolation yet. What I'm going to do now, before we're doing extrapolations, I want to show you the error at this point. So I'm going to subtract t minus, I'll take the absolute value, t minus the exact. Okay, well, it's going to subtract exact from every value of a matrix. So ignore what's over here. Only pay attention to the first column. Okay, right here, we see the error. Notice that the error is decreasing by a factor of roughly 4, which is what we'd expect, because h is decreasing by a factor of 2. This is a second order accurate method, so that amount is squared to get the decrease in the error. And the point is, as we do extrapolations, we expect to see a faster decrease. Okay, so now what I'll do is extrapolation to obtain h to the 4th order accurate approximations. So what I do is, so these first 2 approximations, I'm going to fill in this spot right here. So 2, 2 will be, okay, I'm going to do it this way, splitting instead of having a fraction for everything. So I can take the more accurate value, which is t21, plus the difference of approximations, t of 21 minus t11, all over 3. Okay. All right. Already we see more accuracy. It's got the first 3 decimal places correct. So that helps right there. But now we're going to get more accurate still. So now I move to the second and third extrapolations. So that's good. So I'm going to use ones in rows 2 and 3. So the more accurate one plus the difference of them, more accurate minus less accurate. Again, all over 3. All right, better still. And then one more time. Although, it doesn't look as accurate as I wanted. That's going to bug me, but let's look at the error. Oh, okay then, good. So here we saw the error decreasing by a factor of 4. Look over here. It's hard to tell by looking at numbers, but you see there is a more rapid decrease, definitely more than a factor of 4. It's supposed to be a factor of roughly 16. Why 16? Because that's 2 to the 4th. And look here, like here we had errors 2 times 10 to the minus 3. Now it's 2 times 10 to the minus 6. So it's already literally 1,000 times more accurate. Just from a little bit of work, all this extrapolation, hardly any floating point operations. The trapezoidal rule is one that's more work. And we're getting much more accuracy. So for our computational effort. Okay. But I'm greedy. I want even more accuracy, higher order accurate approximation. So I'm going to continue extrapolating. So I'm going to use my order h to the 4th approximations and extrapolate among them to get 6th order accuracy. Okay. So similar process. But the number of values you get decreases. Here I started with 4, now I get 3. I'll use these 3 to get 2, and then I'll use those 2 to get 1, and then I'm done. So in row 3, column 3, I'll use row 3 and row 2 from the second column, but I have to change my denominator, and the reason for that is if I go back to where we were before, the reason why I multiplied by minus 4 to cancel out the area, the error, is because I had h squared over 4, because it was squared. Now it's going to be raised to the 4th power. So I have h over 2 to the 4th. And you can see how that's going to play out. So can anyone tell me, just take a stab at it, instead of dividing by 3, what do you think I need to divide by instead? If I'm dealing with raising this to the 4th power instead of the 2nd. It's going to be 15. How did you get 15? 2 to the 4th minus 1. So that's what I can divide by. 15. Okay. And E is 1.71828. Okay, we don't have this decimal place right, but we're getting there. And now I'm going to do it again with the approximations in rows 4 and 3. Still dividing by 15. Okay, so now we have more decimal places correct. And now let's look at the error. So we only pay attention to these last 2 entries here in this column. Now I'm going to divide these numbers here so you can see by what factor the error is decreasing. All right, 62.4. When it's a 6th order accurate approximation, you expect the error to decrease by a factor of 2 to the 6, or 64. So that's pretty close. And then finally, we'll extrapolate just one more time these two approximations to get an 8th order accurate, oh, that's supposed to be a comment. All right, so then row 4, column 4. Okay. So what should I divide by here? What? Not quite. 63. Yeah, 2 to the 6 minus 1. So, so 63. Okay, and so now if I look at the error, we only pay attention to the lower right entry. Okay, so that error, let's get an idea of the order of magnitude. 10 to the minus 10. Whereas if we just, here we use the same function values at spacing of 1/8 to get only 2 times 10 to the minus 3 accuracy. Now the error is literally 10 million times less, just by the small number of floating point operations to extrapolate among these values to get these. All right. Okay, so so that's Romberg integration, and what you saw here, like these steps that I took here in Matlab, which you could also do, for instance, on a calculator. There is a problem on the written final where you're carrying this out. Not this many extrapolations, but that's quite a bit of work. Where you would carry a trapezoidal rule to a certain point, and then do a few extrapolations to improve the accuracy. And if you're able to evaluate the integral exactly, you can get an idea of whether your answers are on the right track. So I remember when I took this kind of class way back in 1988 on the final exam, I had to carry out a Romberg integration process. So now, almost 30 years later, you guys get to do that too. So actually, a good idea to review the steps that were taken here in this diary, so you can see the actual numbers that you use, like what do you divide by and so forth. So really what happens is, because the trapezoidal rule has even powers of h in the error, if we look at the algorithm, so our denominators were 2 squared minus 1, 2 to the 4th minus 1, 2 to the 6th minus 1. Well, even powers of h are simply consecutive powers of 4. So that's what I have in the algorithm here, a power of 4 minus 1. And so this is an easier way to remember the formula. It's just a more accurate approximation plus the difference of the two, more accurate minus less accurate, over appropriate power of 4 minus 1. So starting with 3, then 15, then 63, and so on. So something that's not too hard to remember how to do, for instance, if you're working on a paper. Okay. So any questions about the Romberg process? Now, what I'm going to do is I'm actually going to carry out another Romberg process, but I'm going to show you this one because of what happens in it. I'm going to work with a different function for square root of x on the interval 0 to 1. Okay. Now, what's the exact value of the integral? Square root of x, or x to the 1/2. Use your power rule. What's the antiderivative? What? X to the 1/2. That's the integrand, but so what's the antiderivative of that? Not 1/2, but yeah, 3/2. Yeah, 2/3 x to the 3/2. Then you plug in the limits 0 and 1, and you get 2/3. So that's our exact value that we're going for. All right, so what I'm going to do is, if I go back from these commands, so instead of e to the x, I'll do square root. And yes, I could fill in what these are, but I'm lazy. Or I don't feel like doing math in my head right now. So, all right, so 1/2 is our first approximation. And then I'll fill in the other trapezoidal rule ones. So that'd be, okay, fine, square root of 0 is 0. And then square root of 1/2. And then square root of 1 is 1. Okay, and we're supposed to be approaching 0.66667. Already we're off to a not very good start. Okay, now 3, 1. Okay, so now we'll do square root of all of these guys. Okay, so square root 1/4, square root of 1/2, square root of 3/4, and 1. Okay, it's getting better at least, but okay, and then I have, okay, I'm using the recursion formula to make it a little easier. Not so many new function values. Okay, so it is kind of approaching 2/3, but let's look at the error. Only pay attention to the first column because the rest has all these e values in it. Okay, so notice the error is decreasing. That's good. It's not really decreasing by a factor of 4 like we'd expect. So we have more like a factor of 3 roughly in this case. All right, so I figured, well, let's see what extrapolation will do. So for that, I could just use the commands exactly. No change at all. Okay, and then okay, and still not looking all that good. All right, well, at least we have 2 decimal places correct. You know, whoop-de-doo. Yeah, hardly impressive compared to before. And look at this, error decreasing again by a factor of roughly 3. We're not even gaining anything in terms of order of accuracy like we did with e to the x. On the other hand, okay, so then if I complete the Romberg table, okay, after the example of e to the x, we got error 10 to the minus 10. Here we did not even get 3 decimal places correct. It's profoundly disappointing. Okay, now, and I want to check something as for which problems I assigned in this section. 8.6, 1, 2, and 5. So I think I had one in a section related to this, and I don't remember if I assigned it or not. Ah, yes. Well, this is, okay, so I've produced numbers for you, I guess. So this one and this one, but you're still going to write a general function to implement the algorithm. So, but at least you know what you're supposed to get, and then one other function here. Okay, so part of this is to explain. I'll say a little bit more about that in a little bit, but I'm going to give one more contrast. Okay, so square root of x on 0, 1, very bad. Didn't get the order of accuracy we expected at all. But now I'm going to change the example ever so slightly. Square root of x, same integrand, but on a different interval. I'll go from 1 to 2. So my exact value is 2/3 x to the 3/2, but now with limits 1 and 2. So 2 to the 3/2 minus 1. Okay. All right, so this is what I'm going for now. So now if I fill in my Romberg table again, so I have 1 and 2. All right. And then I have 1 plus 2 times the square root of 3/2 and then square root of 2. Now look at the exact 1.218 here at 1.216, already doing pretty well. Okay, and then I'll fix this one. So 1 square root of 5/4, 3/2, 7/4, and square root of 2. All right, that's definitely more promising. And then finally, I have square root of, let's see, 9/8, 11/8, 13/8, 15/8. Okay, so now if I look at the error, now it's decreasing by a factor of 4 again. So it wasn't the integrand alone that was the problem. It was a combination of the integrand that we're using and the interval over which we're integrating. And if I go ahead and carry out the extrapolations, all right, and then look at the error. Again, we get the same kind of impressive results. Look at that error decreasing by a factor of roughly 16, so that our higher order convergence is restored, and that was what we would see if I continued the extrapolation all the way to its end. So all the way to 8th order accuracy. So now we have this error, 10 to the minus 9. See how rapidly the error is decreasing here. Like this is roughly a factor of, well, not quite 64, but it's still better than we saw with square root of x on 0 to 1. So the question is, why does the interval matter? And the key is, well, if the error is large in one case, small in another, examine the error formula. Now, what does the error formula include? There's a constant, there's a higher order derivative, there's a power of h. So you look at, well, what things are the same for one example to another? You could discount those. What's going to be different? And I'm going to remind you of how the error formula came about in the first place. Alrighty. Okay, back in composite rules. Okay, here's where we get the, this is the final error formula right here. So b minus ah squared, an unknown point, f double prime, an unknown point that's somewhere in AB. Now that's your first clue. But another thing to keep in mind is, where we actually got this f double prime at an unknown point, it actually comes from an average of f double prime at a bunch of unknown points. And all of these unknown points lie within their respective subintervals. So the error on each subinterval is determined by the second derivative at an unknown point in that subinterval. So I'm going to make a note of that. Okay, so what we've seen here is, when Romberg works, it works fantastically at reducing error, basically for free, building on what was done for composite trapezoidal rule. So a thing to look at is, note that the error in the composite trapezoidal rule involves f double prime at unknown points within each subinterval, of width h. So take a look at that to get an idea of why everything works quite well for e to the x or square root of x on one interval but not another. What is the second derivative in these cases? Take a look at that. Okay, so that should help you with that exploration, and then Bless you. Enjoy your Thanksgiving. Feel better. And well, 'tis the season to get sick. And we'll have the last topic in a week.
You are the only participant.
I saw a typo on the thing.
Oh,
The Lagrange has 3 0 0 0 0.
oh, I'm not surprised. So,
Yeah.
okay, yeah, go ahead and send it to me. And
Yeah, one was scaled in 2009 and this one.
oh, dang. Okay. Well, at least I'm consistent.